Hi everyone, the topic I want to talk about today is Big O. What is Big O? Big O notation is used extensively to estimate the number of operations on algorithm uses as its input grows. So we can use Big O notation to compare two or more algorithms to determine whether it is more efficient as the size of the input grows. For example, if first algorithm is n and another algorithm is n to the power of 7, then we can see that the first algorithm is user far fewer operation when n is large, like we can take n equal to 100 or 1000. Let's see the definition of Big O. Let f and g be functions from the set of integers or the set of the real numbers to the set of the real numbers. We said that fx is Big O of gx if there are positive constants c and k such that fx smaller than or equal to cgx whenever x bigger than k. In spoken English, we say fx is Big O of gx. Two logical equivalent. First is fx is Big O of gx. This means assist k and c for all x bigger than k imply fx smaller than or equal to cgx. The second one is negation of the first one. Negation of assist is or. The negation of or is assist. Then we can think this is the p and implied q. So negation of p and implied q is p and dot q. The constants c and k are known as the witness to the relationship fx is the Big O of gx. And this is the some definition of fx is Big O of gx. And we often use the way is fx in this way to express the fx is the Big O of gx. Okay, let's see example 1. So fx is Big O of x to the power of 7. By calculation, 2x to the power of 7 is already same size as x to the power of 7 for all x. This sign means same size as. When 23 x to the power of 6 is smaller than or equal to x to the power of 7, x must be bigger than 23, and the rest is used the same way. We find x also bigger than 1. We choose the maximum number of them is 23 for k. When x is bigger than 23, then this or is smaller than or equal to this, because 2x to the power of 7 is same as 2x to the power of 7, and the rest is smaller than or equal to x to the power of 7. Then add it together, we get 6x to the power of 7. So we choose c is equal to 6. Choose c equal to 6 and k equal to 23. We assume x bigger than 23, then we get the or term is smaller than or equal to x to the power of 7. So fx equal to this is smaller than equal to 6x to the power of 7. How to get x to x to the power of 7, and then rest is x to the power of 7, 2, 3, 4, 5, 6. So therefore fx smaller than or equal to 6x to the power of 7. So fx is Big O of gx. Then fx is this polynomial, and gx if gx is the x to the power of 7. Okay. Example 2. So that x cubed x squared is Big O of x cubed. By calculation, x squared smaller than or equal to x cubed. So x must be bigger than 1. We choose k equal to 1 and c equal to 1. Choose k equal to 1 and c equal to 1. We assume x bigger than 1 multiplying by x squared on both sides. We get x cubed bigger than or equal to x squared. Therefore, we get x squared smaller than or equal to x cubed. So x squared is Big O of x cubed. We also can choose the largest value sk and c. Example 3. It's true that x cubed is bigger of x squared. We do not sure, so we can do investigation to see what happened. We choose some number that like 1000, 10,000 or 100,000 or more, but here we choose 3 only. We can see x cubed is always bigger than x squared. This suggests x cubed is not bigger of x squared. We can use this equivalent to prove let k and c be positive real number. We choose x equal to c plus k. Then x bigger than k, also x bigger than c, multiplying by x squared to get x cubed bigger than c x squared. Thus x bigger than k and x cubed bigger than cx squared is true. Therefore, x cubed is not bigger of x squared. This is important. F is bigger of G is not necessarily equal to G is bigger of F. From the previous example, we know that x squared is bigger of x cubed, but x cubed is not bigger of x squared. We can see these two, and then of course there have a possible that F is bigger of G is equal to G is bigger of F, like these two examples. Let fx be a polynomial of degree n, then fx is a big O of n to x to the power of n. Let fx be a polynomial for real number at 0 to n. Choose k equal to 1, c equal to absolute of this. Then assume x bigger than 1, then x to the power of j is smaller than or equal to x to the power of n for j equal to 0 to n. So fx smaller than or equal to fx absolute of fx and smaller than or equal to this, and then this also smaller than or equal to this because Sn is bigger than always bigger than the rest. So take out the x to the power of n, we get this bracket is c. So fx smaller than or equal to cx to the power of n. So 4. So that n factorial in O big O of n to the power of 7 and log n factorial in is big O of 7 and log n. Okay, we separate the question. First is we choose k equal to 1, c equal to 1, assume n bigger than 1. So n factorial is 1 times 2 times 3 until times n. We also can say this smaller than or equal to n to the power of n. So we can prove that n factorial is smaller than or equal to n to the power of n, then smaller than or equal to n to the power of n bracket to the power of 7. This so n factorial is bigger of n to the power of 7. Choose k equal to 1 and c also equal to 1. Assume n equal to bigger than 1 from above. N factorial is smaller than or equal to n to the power of 7. We take log of both sides. We get this 2, and then log n to the power of 7n is 7n log n. So we can prove that log n factorial is bigger of 7n log n. Relationship. This is compared with the polynomial and polynomial. So the degree of this is bigger than this, so n to the power of c is bigger of n to the power of d. This is a log function and this is a polynomial function. Log function is the bigger of polynomial function. This is the polynomial function and this is an exponential function. So polynomial function is bigger of exponential function. Two exponential function we want to compare is c, the base 1. So b is smaller than c, so b to the power of n is the big O of c to the power of n. And the exponential function and factorial function, we can say that exponential function is always big O of factorial function. For example 5, arrange that function f1 to f7 in a list so that each function is a big O of that function. So we can see the slowest one is the constant function, so put 1, and next is the log function because log is slower than the polynomial function. This is the polynomial function is of degree half, and then the degree 1 and the degree 7 here. So this and degree half, degree 1 and degree 7, and then the exponential function, and the faster one is factorial function. Okay. This picture can make it easier for us to understand who is slow and who is fast. So that f1 is big O of g1 and that f2 is big O of g2. Then f1 plus f2 is big O of g, where gx is maximum of g1 and g2. Assume f1 is big O of g1 and f2 is big O of g2. So we have two equivalent. The important is k and c is different in both because they exist, but x is not need to differ because it's for all x. So we have these inequalities, then these inequalities can be equal smaller or smaller than or equal to this maximum. Then this also can be this 2 times maximum c1 c2 times maximum g1 g2. This is equal to this, and then we choose k and c for all x bigger than k, implying f1 plus f2 smaller than or equal to cgx. So we prove corollary if f1 and f2 are both big O of gx, then f1 plus f2 is also big O of gx. This is some example. Okay, last theorem. Suppose that f1 is big O of g1 and that f2 is big O of g2, then f1 times f2 is big O of g1 times fg2. Assume f1 is big O of g1 and f2 is big O of g2. So we have the two equivalence. So this is important for axis and or axis is different. This is important. So next we choose k equal to max k1 and k2 and c equal to c1 times c2. If x bigger than k, then x bigger than k1 and x bigger than k2. So we have this inequality. So multiplying the inequality, the two inequality multiplying together, we get f1 f2 smaller than or equal to c1 c2 times g1 times g2 equal to c g1 times g2. Therefore f1 f times f2 is the big O of g1 times g2. Example 6. Give a big O estimate for fn equal to 23 n log n plus n minus 3 square log n, where n is the positive integer. 23 log n is big O of n log n, and n minus 3 square log n is big O of n square log n, because by the previous theorem we can see this is a degree of 2, and so we want to take a degree of 2 to be a big O. So 23 n log n and n minus 3 square log n is big O of n square log n. We can see the graph. This is separate. When separate, this the graph n square log n is faster than this two. When add together, n square log n is also faster than this two. Thank you very much for your watching and listening. This material are taken from this reference.